Hello everyone. In this part 3, we are going to study the partial differential equations. First chapter is orthogonal function and the Fourier series. Second chapter is the boundary value problems in rectangular coordinate. Third chapter is the boundary value problems in other coordinate systems. Last chapter is integral transform. First chapter is orthogonal functions and the Fourier series. In the first section, we are going to define the orthogonal functions. Second section is a Fourier series. Third section is a boundary value problems. Last section is a Bessel and Legendre series. First of all, we'd like to define the orthogonal functions. To find the orthogonal functions, we need to define the inner product of functions. So this is the definition of the inner product of the two functions. So f sub 1 and f sub 2, lower limit is a and upper limit is b. And the product of the two functions we'd like to consider f sub 1 and f sub 2. Then we perform the integral to find the inner product of the two functions. When that inner product of the two functions becomes 0, then we call the two functions is orthogonal. A set of functions becomes an orthogonal set if you pick up the two functions from the set. Then take an inner product of the two functions is 0. Then we could say that a set of functions becomes an orthogonal set. Now we'd like to define the norm and the orthonormal set. Norm of a function is defined. Take an inner product of the function itself. So we consider the norm of the function phi sub I is expressed the inner product of the function phi sub I with itself. So it becomes phi sub I squares. Then take a square root to find out the norm of a functions. Orthonormal set of functions is an orthogonal set of functions with unit norms. Each function in a set has a magnitude of 1. Then we could say the orthonormal set of functions. A set of functions becomes an orthonormal set by dividing each term by the norm as phi sub 0 divided by the norm of a function of phi sub 0. Also phi sub 1 divided by the norm of the phi sub 1. So we could derive the orthonormal set of functions from the orthogonal set of functions. I'd like to explain the important expansions, orthogonal series expansions. We use a set of orthogonal functions phi sub 0, phi sub 1, phi sub 2 on the interval a to the b and expand the functions with a set of orthogonal functions as fx is c sub 0 times phi sub 0 plus c sub 1 phi sub 1 plus c sub 2 phi sub 2 blah 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 blah. Function of f is expressed c sub 0 phi sub 0 c sub 1 phi sub 1 plus c sub 2 phi sub 2 plus c sub 3 phi sub 3. In general, blah blah blah, in general, c sub j phi sub j plus blah blah blah. Then we take a inner product with phi sub I in the both sides of the equation. So multiply the phi sub I the both sides of the equations. So it becomes phi sub I fx integrate a to the b dx equal c sub 0 is a constant a to the b phi sub I phi sub 0 dx plus c sub 1 a to the b phi sub I phi sub 1 dx plus blah 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 plus c sub j phi sub I phi sub j dx plus blah blah blah. Then for the right hand side, it becomes c sub 0, phi sub 0, phi sub I, plus c sub 1, phi sub 1, phi sub I, plus blah blah blah, plus c sub j, phi sub j, phi sub I, plus blah blah blah. Phi is a set of the orthogonal functions. If the j is not equal to the I, it becomes 0. By considering the orthogonality of the set of functions we obtained, except the single terms, all the terms become 0. If the I is not equal to the 0 or I is not equal to 1, then it becomes 0. If the I is equal to the j, this becomes a to the b phi sub I squares dx. So it becomes a norm of these functions. So c sub I is expressed integral of the fx phi sub ix over square of the norms of the phi sub i's. C sub I is expressed inner product of the f and the phi sub I over the square norm of phi sub I. So you can substitute this c sub I into the expression for the f. So fx is a c sub I phi sub I is 0 to the infinities. You can substitute this c sub I to find the expressions for the fx. Sometimes a set of functions phi sub 0, phi sub 1, phi sub 2 becomes orthogonal with respect to the w. On the interval a to the b, we need to multiply the w. Product of the phi sub I, phi sub j becomes 0 when the I is not equal to the j. The function is expressed with this set of functions phi sub 0, phi sub 1, phi sub 2. Because fx is expressed I equals 0 to the infinity c sub y phi sub I. Then we need to multiply the wx and the phi sub j x fx dx and integrate a to the b. And both sides c sub I integrate a to the b wx phi sub I phi sub j x phi sub I x dx. We use these relations. Then except the single terms, all the terms become 0. So that term is given the I equal j. So you can substitute I is equal to j. A b wx phi sub jx squares dx. So from these equations, you can find the c sub j is expressed integral a to the b wx phi sub j x fx dx over integral a to the b wx phi sub j squares dx. So we find the coefficient of the c sub j. And by substituting this c sub j into these equations, you will get this expression for f. Okay, this is the end of the first session.